Irrational numbers. Irrational numbers, which don't have a symbol of their own, they're just not Q, are numbers that cannot be written as a fraction. As a decimal, they would not be terminating or exhibit any pattern, and an example is pi. Prove that root 3 is an irrational number. This is a proof that is normally done by contradiction. So we'd start by assuming that it can be. So root 3 is equal to a over b. We have to have a and b belonging to the set of integers, and we may as well say positive integers since root 3 is a positive number. And a and b have no common factors. In other words, what we're dealing with here is a fully cancelled down fraction. Now let's square both sides. So 3 would be a squared over b squared. That means that 3b squared is equal to a squared. That means that a squared is a multiple of 3. And the only way that that can happen is if a is a multiple of 3. Let's say that it's 3c, where c is also an integer. Then 3b squared would be equal to 3c all squared. So 3b squared is 9c squared, and therefore b squared is equal to 3c squared. Therefore b squared is a multiple of 3, and that means that b is a multiple of 3, and that's a contradiction because we assumed they had no common factors, but we've shown that they both have a factor of 3. Prove that log to the base 3 of 10 is an irrational number. Once again, contradiction is a good way of doing this. So let's assume that it can. Log to the base 3 of 10 equals a over b. A and b, we can say, are positive integers, and a and b have no common factors. So it's a fully cancelled down fraction. Now, we know when dealing with logarithms that if a to the b is equal to c, then log to the base a of c is equal to b. So what we can say here is that 3 to the power of a over b is equal to 10. Raise both sides to the power b. That gives us 3 to the a is equal to 10 to the b. Now this cannot happen. 3 to the power 1 is 3. 3 squared is 9. 3 cubed is 27. 3 to the 4 is 81. 3 to the 5 is 243. All powers of 3 end in a 3, a 9, a 7, or a 1. 10 to the b has to end in a 0. So these two things cannot be equal, and we have, once again, a contradiction. We want to construct the decimal 0.001, 0001, 00001, and so on by adding fractions of the form 10 over 3 plus a, where a is a positive integer, or 0. So let's just look at our 0.001, 0001, 0.00001, and so on. That's equal to 0.001 plus 0.0000001, and then we have 0. We need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. And a 1, and so on. So this is 10 to the negative 3. Add 1, 2, 3, 4, 5, 6, 7. 10 to the negative 7. Add 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 10 to the negative 12. And we can see the pattern here. This has gone down by 4, then by 5. So the next one would be 10 to the negative 18, and so on. So we can say that's 1 over 10 cubed, plus 1 over 10 to the 7, plus 1 over 10 to the 12, plus 1 over 10 to the 18. If we add 7 to that, the next one will be 1 over 10 to the 25, and so on. Now, let's see if we can come up with a general expression. So, the power here was 3, the next one's 7, the next one's 12, then 18, then 25, and if we go for first differences, that's 4, 5, 6, 7. Second differences are going to be 1, 1 and 1. So we have a constant second difference telling us our formula is of the type an squared plus bn plus c. Counting back by 1 here, so we can see these differences are going down each time. So that would mean that this was 0, and that tells us that c is 0. This constant difference of 1 tells us that a is a half, so it's a half n squared plus bn. Let's just use another value from the table. Let's use this one. So we would need a half of 2 squared plus 2b is equal to 7. So 2 squared is 4, half that's 2 plus 2b is 7, gives us 2b is equal to 5, so b is 5 over 2. So the general formula for these fractions would be 10 to the power of 1/2 n squared plus 5 over 2 n, where of course n is a positive integer, and we can now do this exercise 7.05 on page 264.